So please be aware that the video will be recorded and it will be edited and uploaded to the Husky City website. But please be aware because due to the recent server overload, so the WebEx server is overload. So sometimes the retrieval of the video may be delayed. And yeah, so there will be take some time. So for the expectation maximization, so I will upload it this weekend. So please stay tuned. I will also send a notice when the video is recorded and uploaded. Yeah, thank you for the reminder, Kai. Okay, so let's begin today's lecture. So today we will go to an exciting topic. There's a so-called the dimensionality reductions. So I believe some of you have already have some basic ideas about dimensionality. So we will talk about more about its importance and why we need to do the reductions here. Okay, so before we start, so this is the reading materials that I would like to recommend you to read. So for the data mining, that is you need to look at the chapter 3.4.3. So for the two textbooks, data mining and also the introduction to data mining, the description about the principal component analysis or PCA is not very detailed. So I also recommend you to look at this book. It's the hands-on machine learning that I mentioned earlier during the beginning of this semester. So you can look at the chapter 8, which is the PCA. So it has a very detailed description about the PCA and also some implementation on how you can use the Python to conduct the PCA. So we will also talk a little bit about that later. So this is today's outline. So I will talk about the motivation of conducting the PCA and also how we can conduct feature selection and also the principal component analysis. So these tools are the basic topic that we will talk about today. And most important one that is the PCA. So please be aware that I will also give some exercise, assignments, and also the exams. We'll talk about that. So I hope that you can pay attention to this particular section. So dimensionality is how it does is like we have a vector X and we try to find the functions, certain algorithms or certain models or certain mechanisms and transform the input vector X into another output vector Z. So basically that is for the input vector X, it will have very high dimensions. So here the dimensions can be so-called the number of the attributes. So as we mentioned in the data preprocessing, so every data point, it may be described in multiple different attributes. Say when we describe a person, we can use age, gender, and many other properties or attributes to describe a person. So each attribute will consider as a dimension. And sometimes we may encounter the data set where the input vector would be of high dimension, meaning that it will have very high dimension and we need to reduce it into a lower dimensions. So this is particularly important in many scenarios. Say, for example, we are given a high dimensional data set. We would like to visualize it or better understand how the different data points are displayed or distributed. So sometimes we need to do it in say like a dimensionality reductions from the three-dimensional space into a two-dimensional space so that we can display it in a 2D map or plot it in our screens to better visualize that. And that would be very important for us to understand how those data points are distributed on the screen. So this is a basic intuition about conducting the dimensionality reductions or dimension reductions. So actually, in terms of the dimensionality reductions, there's a so-called theory called the curse of the dimensionality. So, sorry, there's some. Screen is okay. So the theory called the curse of the dimensionality is say that if we have too high dimensions about the data set, it will be very difficult for us to understand and describe the data set. And there are a lot of different kind of explanations about this theory. So say there's like, if we are considering a 0 dimensions, meaning that there's no attributes, and if we only plot a point in a space, that is very easy for us to describe that and understand that. But if we have, say, 1 dimensions, the data point has 1 attribute, and the data point can move along a straight lines in the space, then we can search the data point along this straight line and find this data point or describe this data point. So there's 1 dimension case. And in 2 dimension space case, then for each data point, then we have 2 directions to search that. So we can imagine there's like a grid here. So every data point can be lies upon the grid here and traverse against two directions, from X or from Y. And we can search that data point from these 2 directions. But from the 3 dimensions, we add the new dimension, say the Z. Then when we search for that data point, then we need to traverse 3 directions, X, Y, and Z. And if we have 4 dimensions or even higher, so say, imagine, so I believe some of you, or probably most of you, have seen the movie called The Interstellar. So in that movie, at the end, the character went to a space, which is high dimensional space, say 4 dimensional space, where a new dimension called the time is added towards that space. So it's very difficult for us, for the common human beings, to understand that space. So we add a new space, and when add the new dimensions in that space, and when we would like to traverse the entire space, we need to search along the 4 dimensions beyond X, Y, Z, and even the 4th dimension. Say in that movie Interstellar, is the time. So we add a new dimensions to search the data point. So in high dimensional space, the data points, we will see that it will be very difficult for us to search along different directions because the dimension has been very high. And the data point, you can imagine, that will be very, very sparse because the mutual distance can be very far away due to very high dimensions. And most of the data points, they will be likely very far away from each other. So when we would like to describe such a kind of space, then the dimension is an important factors that we need to take into account. And that's why we have the so-called curse of the dimensionality, in order to see whether we can reduce the dimensions and improve the descriptions or representation of the space. Say, if we want to visualize the data point, maybe we need to plot it in a 3D dimensions, not those dimensions beyond the 3, because that would be beyond the normal understanding of our human beings. So actually, there will be a lot of different importance about the dimensionality reductions. Say we can reduce the time complexity. It's very simple to understand because say we are calculating the distance between the data points, the more dimensions, then the more calculation we need to do. So reduce the time complexity, that would be also important. And of course, in terms of the space, it can also help us to reduce the space complexity, and we need less parameters to describe the data point. And also, it will save the cost of observing the feature, because when we would like to search along the entire space to find the data point, we can look at fewer dimensions to search for data points, and it will save the cost in observing those features of the data point. And of course, with the simpler data points, then we can use simpler model to describe those data sets. And using the simpler models sometimes will be more robust on the small data sets. And it is easier for us to visualize. Say if we are using the 2D dimension to describe the data point, it will be easier for us to interpret the result of the data set, and also it will lead to simpler explanations. And of course, we will see some of the example, that is the data visualization. We have a simpler model using 2 dimensions or 3 dimensions to describe the data set, so that we can derive some interesting observations from the data set from a simpler visualization or easy to understand visualization. So let's see how we can conduct the feature selections or the dimensionality reductions. So the first and the simplest way that is so-called feature selections. The basic idea is try to select the k dimension or k important features and ignore the rest of them. Say that is, if we have total d dimensions and we select only k and ignore the rest d minus k dimensions, then we can use some selection algorithms to find those features. And the second part of the dimensionality reduction is so-called feature extractions. So we will not just focus upon the using certain features, certain subset of the entire data points feature set, but we focus upon whether we can extract some features. So those features, they may not necessarily to be the concrete features that we observe from the original data point, but they have some projections, distortions, and they will change. And we extract the new features from the original feature set. So it's a kind of projections, and we will see that it still can project the data point into a space with the fewer dimensions. And we call it the so-called principal component analysis, or PCA for short. So we will see how these algorithms work. And the first one, let's talk about the feature selection. It is a very simple one. So basically, it is if we have D features, and then when we try to conduct the feature selections, and there are total 2 to the power of the D. Of course, we can use 2 to the power of the D minus 1 because the 0 features means nothing. So we can use the D 2 to the power of the D subsets of the features to figure out what would be the best subset for the entire data set. We can conduct the both way to search for this kind of the subset. One is so-called a forward search. So we start from the 0. Say we start from the 0, we one by one add a new features and look at a certain metric and then to see what kind of the subset that we should decide. So it's a kind of forward search that try to add the best feature at each step. It's an iterative process, and sometimes we can observe, say, like a certain performance metrics will converge, and then we decide that, well, this subset of the feature should be selected. So this is the forward search method. And another one is a reverse way, the so-called backward search. We start from the total D dimensions, the original dimension space, and we start to remove a certain features, and we step by step to look at whether the convergence of the performance metrics will also be observed. And then we stop such a kind of removal process or pruning process. So forward search is to add the features, and the backward search is to remove certain set of the features. So these tools are similar way, but we need to be careful about how we can design certain kind of performance metrics, say the objective functions. So it has multiple different ways to evaluate that, and it highly depends on the application scenarios. We can use, say, the so-called interclass distance. The class here meaning it's like the different labels. So we have not yet talked about classification yet. We will talk about classification later, but the basic idea say is if we have multiple different categories of the data set, say there's like we are studying about the animal data set, and animals have, say, like a cat, dogs, elephants, different kind of animals, and different kinds of animal can serve as different kind of labels. So the distance between different labels or different classes can be considered as a kind of the objective functions here. And also there is the statistical dependence between those different features. Okay, say, yeah, like if we know that some of the features, they may have some correlations, meaning that if one feature has some increase or decrease trend, we can also observe some similar increase or decrease trend on another dimensions. So in such a kind of in such a kind of scenarios, mean that probably these two dimensions, we only need to consider one of them, and the other one is redundant and can be removed. So such kind of statistical dependence can be also observed through some kind of metric, and we can use such kind of metric to remove those redundant features. And of course, there are some other measures like information theoretical measures, or some more straightforward is if we have certain kind of models, and we can use those generated subset of the features to predict or classify against a certain data set, like a test data set, and to see whether the prediction accuracy is high enough or the error has been low enough, and then we decide that the subset of the features is the best one. So these are all the kind of the engineering process, and it relies a lot of effort on studying such kind of the different objective functions. And you can also look at those references that I have provided in the reading materials. But these are all very complicated, in fact, because it really requires a lot of tuning. And sometimes we may not be able to interpret the result a lot. And sometimes if you take a lot of effort, say, for example, every time we need to predict against a certain kind of data set, and it will cost a lot of time when we select such kind of subset of the features. And as I said, the entire subset will contain 2 to the power of the d. So if the d is very large, say if we are looking at like the gene data or biomedical data, those dimensions can be very high, and those subsets will be very exhaustive to search. So that's why people have considered whether we can use some algorithms to automatically select the subset of the features, or try to identify those features that we can use for the machine learning or big data analysis. So that's why people consider some other more advanced way, say the feature extractions. That is like using some projections way to try to retrieve those useful features in a certain kind of the combinations of the original features. That is why we call it the feature extractions, and typical one that is the PCA. We will talk about it in the following few slides. So the PCA starts from the observations about the covariance. So covariance is a kind of way to describe the variance within the data set, and also the covariance across its multiple different dimensions. Let's see how it is calculated. Say if we are given 2D data points, and the covariance of the entire 2D data points data set can be described as this formula. So its diagonal elements are the variance of the data within each of the dimensions. Say if we have the x and y to describe the entire data set, x is, say, the horizontal axis and y is the vertical axis, then we can calculate the variance with respect to each of the dimensions. That is, we have the variance of x, that is the variance along the x-axis, the x dimension, and the variance of y, that is the variance along the y-axis or y dimensions. And we can also calculate the covariance between the x and y. So x and y will be placed here, and we got the covariance of the entire data set. So I will let you know how we can calculate the covariance later from some simple example. But let's look at how the covariance will look like for different data sets. So for example, we can see this data set, it has this kind of the distributions. And when we look at the covariance, we can see that it's the variance along the x, that is the 2, and variance along y is 3. And we can see the covariance between x and y. So because it's a symmetric, so covariance between x and y is equal to covariance between y and x. So it's 0.4 here, and it is much smaller compared with the x and y. But x and y's variance, they have similar scale. So we can see the entire data point is like pointing towards. So Kyle's question is, will covariant x and covariant x and y, covariant y and x always be the same? And yes, you will see the equation on how it is calculated. Yeah. So it depends on the data set. So if we normalize the say all the data points, so the values will be the same. So let's see the formula later. on how they will be the equal. Yeah. So let's see this example here. The entire trend of the data point, so it's pointing towards these directions, meaning there's like a X and Y, they have very similar span. And the entire spans along this direction is the longest one. So we can see the entire data point along these directions, their spread is the largest one because the X and Y, their variance are very similar. But when we look at this data set, that would be very interesting to see that it's like comparing the variance between X and Y. X is much smaller compared with the Y, meaning that the data point in terms of the variance across or the spans across the X dimension is pretty small. But in terms of the Y dimension, it's pretty large. And we also see that is the covariance here. So its approximation is around 0, meaning that there is very little correlations between the X and Y. So it is a kind of this kind of the span here. And similarly for this, it is like we can observe very small spans across the Y directions, but very large spans across X dimensions. And the covariance between X and Y is pretty small. And this way, this example is a reverse way compared with this one. There's like we can see the covariance between X and Y is minus, meaning that they have some negative correlations. So when X increase, the Y will decrease. So it's a kind of pointing towards these directions, and the spans along these directions is the maximum one. And we can still observe that it's like in terms of the X variance is very large, while the Y variance is pretty small. And meaning that the entire data set is spanning more against the X dimensions, but it is pointing towards these directions, meaning that the data points or the dimension between Y and X, they have some negative correlations. So meaning that the correlations or the covariance will help us to better understand how the entire data point is distributed. And when we would like to describe the spread or the variance of the data set, it would be great that we can find these directions where the entire data set is spreading with the maximum spread or the maximum level. So this direction is what we are interested in. And maybe that will help us to better reduce the dimensions, say from a high dimension to the dimension where we can describe the data with a very maximum spread, so that we can distinctively recognize each data point and differentiate their location in the entire space. So that is the kind of motivation that we will need to use the covariance for the PCA analysis. So let's see the principal component analysis. So it will try to find projections that captures the largest amount of the spread of the entire data set, or the largest amount of the variations. Say if we have the data points consist of the X1 dimensions and the X2 dimensions, and we have those data points, we would like to find out these directions or a projection space where every data point will be projected towards these directions, and it will have the maximum spread along the entire directions. And the original data sets, they will be projected to this smaller space, and then we can conduct the so-called dimensionality reductions. And these directions will rely on the so-called eigenvectors. So this eigenvector will help us to better describe these directions. And these directions is based on the covariance matrix that we have observed from our previous slide. And these eigenvectors will define these directions. And we will see some of those examples later. So let's see what this PCA is working. So it's based on the so-called eigen decompositions. So eigen decomposition will return two important outputs. First one is so-called eigenvectors. And in terms of the PCA, is corresponding the principal component. So it determines the directions of the new feature space. So this will be important for us to define the space that we need to project the data towards to. And the eigenvalues is the values that will determine their magnitude. So the larger the eigenvalues, meaning that the spread will be large. So in other words, it will explain the variance of the data along the new feature space. So if we project the data point towards this principal component, and then the entire spread will be described based on these eigenvalues. And we will see some of the examples in some figures. And let's figure out how we can calculate the eigenvectors and eigenvalue first. So let's look at the definitions. So definitions about the eigenvector is as follows. So say if we are given a vector, certain vectors, if it have the same directions as the product between a certain matrix A and this vector, then we can call this X, the vector, is the eigenvectors of this particular matrix. And please be aware this our matrix A is a symmetric matrix. So it can be the n times n matrix, where n is the, say, for example, the number of the dimensions we are considering about. So this A can be the corresponding covariance matrix of the data point. And we know that the covariance matrix, if it have, say, like an n dimensions, then the covariance matrix will be the m times m matrix, which is a symmetric one. And that is the definition of the eigenvectors. So in the equation representations, we can say there's the AX equals to lambda x. So here the product of the between the matrix A and the vector of x is equal to a certain kind of scalar times this vector. And meaning that when we use the product between these two, it will lead to the same directions as the original vector x. So the lambda here will become the so-called eigenvalues. So it describes the entire scale of this kind of projections. So if we consider the kind of the like matrix into space, so AX is a kind of the projections of the original data set. So it will lead to another vector, is the lambda x, and the lambda describes the scale, or we can say that's the variance of the data point along these directions. So if we use a certain kind of vectors and times these projections of this certain matrix, and it will lead to a certain kind of the same vector, but of different scales. So this lambda is the scale to describe the entire projections, and it will become the eigenvalue associated with this matrix X. And we can do some simple math and transform it into this part, as we would like to calculate the find out the corresponding value for the lambda. So we use the determine here, because if a certain matrix times a vector equals to 0, and because the eigenvector itself cannot be 0, and therefore we need to make sure the determinant of the left-hand side, which is the A minus lambda I, is its determinant is 0. So the question is the eigenvalue a constant? Yes, it's a scalar, and it is associated with the corresponding x. So every lambda will correspond to a certain eigenvector x. So for example, for each input A, it will have potentially multiple different eigenvalues because it may have multiple different projections. And for each projections, it will have different spread. So for each projections, we will find the corresponding spread. And during this process, we will first determine the eigenvalue, which is the spread. And when we find out these formulas and we do the simple math and take the determinant for the left-hand side, which is the A minus lambda I. I is the identity matrix. And then we make sure that we can calculate the corresponding lambda first. So that is the first step on the eigen decomposition. That is, first we look at the eigenvalues. So let's see the first examples. So very simple examples. There's, the question is to show that this vector is the x is the eigenvector for the matrix A. So matrix A is given as here. That is a 2 times 2 matrix. It may not be symmetric, but it is fine because eigen decomposition can be applied to the matrix, and that matrix does not necessarily to be symmetric. Then we try to prove that this is the eigenvector for this matrix. We first look at the definition. There's AX equals to lambda X. So we put AX, that is we find the product between this matrix and the vector, and we see that it output the 0 vector. There's 0 vector here. We also see that if we let X lambda to be 0, then we use the 0 times this vector. It's also 0. There's a 0 vector, meaning that AX is equal to lambda X. So it satisfies the definition of the eigenvector and eigenvalues. And therefore, we can conclude that the X is an eigenvector or eigenvector of A, and the lambda equals to 0 is an eigenvalue for this matrix A. So that is the definition and also how it may be calculated here. But we will see how those principal component analysis will use such kind of example. So let's look at two further other examples on how to find out the eigenvalues. So eigenvalues is the first step because it's easier for us to calculate. So we first find out the eigenvalues and then determine the eigenvectors. So let's see some examples on how to find out those eigenvalues. So this is also very important, and it will be tested in the, like say, the exams or the assignments. So please be aware. So say we are given the eigenvalue A equals to this matrix, and we first try to find out the eigenvalues. So we will look at the AX equals to lambda X, and we try to look at the A minus lambda I times X equals to 0. It's a simple math because we need to move this part towards the left, and then we decide the determinant of A minus lambda I equals to 0. So determinant is given as left-hand side. So it's fine that we write it in lambda I minus A, and we make the determinant into 0. So the lambda I minus A, so I is the identity matrix that is see as here. That's like so the diagonal elements, they are all 1, but they are off diagonal elements, they are all 0. So lambda I minus A is equals to, say, this the element here is like as follow. And when we determine the determinant, so the determinant is this element here times this element minus the product of the other elements. That's the minus 1 and 12. That's the can be seen as here. That is the minus lambda minus 2 times lambda plus 5 plus the 12. So that is the determinant of this matrix. And then we make it as 0, and then use some simple calculations, and then we can make sure that this part is equals to 0, and therefore lambda can be either minus 1 or minus 2. So that is the basic process of the calculating the two eigenvalues for this input matrix A. But of course, it can be applied to higher dimensions. Say if we have the higher dimensions and the input matrix A has, say, like a 3 times 3 matrix. And then when we would like to find the eigenvalues, is also similarly, it is conducted is the determinant of the lambda times A minus A, and we make the determinant as 0. And then we can decide that is make it as a 0 and then return the corresponding eigenvalues here. It's also as shown here. And please note that if all those eigenvalues, they are the same, and we can call it that is the eigenvalues is said to be of multiplicity K. So here this lambda equals to 2 is an eigenvector of multiplicity 3 here, meaning that there are 3 eigenvalues and they are the same as the value of 2. So that is a kind of process of calculating the eigenvalues here. So you can practice this part after your lecture. And then given this part, that is, we already find out the corresponding eigenvalues, and then we look back upon the vectors that we are talking about. That's the eigenvectors. So once we got the eigenvalues lambdas, then we can solve the x through the above equations. And it's a kind of solving a linear systems using some back substitutions. And we will show simple examples with our later slide. But before that, I would like to first talk about the PCA, that is the theory behind the PCA, and why it is relying upon the so-called eigenvector decompositions. So back to our original definition, that is, given the set of the data point S, and we would like to try to find a low dimensional space such that when the S is projected there, the information loss is minimized. And intuitive understanding is try to see whether the variance or the spread of the entire data point is still preserved. Say if we have those data points and they are spreading like this way, and if we are trying to project the data point all towards these directions, and they are spread along this direction, is matching the original spread of the data points. And it is the best way to describe the data sets, even though they have been projected to a new space, meaning that's the minimize the entire information loss. So the projection itself can be described as follows. So the new projected data can be described as the product between the W and the original data set. So the W here is the certain kind of vector that can project the original data set into a new space. And the problem that is try to see whether we can find such a kind of the vector, projection vector, such that the entire variance of the Z, that is the new data. So the T is the transpose. T is the transpose. You can check the definitions online. So this transpose is transposed upon certain kind of the matrix or vector. So the entire objective of the PCA is try to maximize this projected variance. Projected variance maximize, and then meaning that we preserve the original spread. And the theory here is the variance here, and we can prove that is equals to this the covariance matrix happens to the covariance matrix of, thank you, Christian. Thank you for your answers. So the variance of Z can be proved as there's the W transpose times the covariance of the W, and the W here is actually what we are interested in. So we can follow these following equations and prove that the variance of the projection is equals to the this product here. And we also know that it's the variance of the original data set is covariance is actually the covariance matrix here. So you can practice this part after the lectures. And actually, so when we are looking into this problem, PCA is try to see whether we can maximize the projected variance. And of course, there may be some kind of the constraint here. Sometimes we would like to see whether this determinant or the norm of these new vectors is actually 1, meaning that we would like to use a normalized vector to project the entire space so that the scales will not be changed a lot after the projections. So we will constrain this part. So if you know something about the optimizations, so we can use the so-called Lagrange multiplier to solve this kind of optimization problem. That is, we will convert it into a form that is try to maximize the objective functions minus the alpha times the constraint here. So please be aware these are all the theory. It's not required in our class, but it will be provided here to help you to better understand why we are using the eigenvector for the PCA here. So when we are using the Lagrangian multiplier, so we will got the objective function is try to maximize this one. So we can use some kind of the derivative upon this entire formula. So the base idea, say, for example, if we are considering a space, if the function is convex, and the convex functions will often look like a shape like this, and the maximum data point is usually along the top, and where the derivative of this data point is 0. So meaning this, if we use the function of w here, and we describe the entire function of fw, and if we would like to find out a certain data point omega, so that the entire values of the f omega is maximum, then we will use the derivative. Let's try to derivative and divide with respect to the x omega here and make it as 0. So for this part, we know that the sigma here is a constant, and then we will use the derivative, and we will find that the derivative of this formula fw here is equals to 2 sigmas minus 2 alpha omega. And because this part is constant and it will become 0, and this is the derivative of the f omega against the omega, and we will make it as 0 here, and therefore we will got the formula that is the sigma omega equals to alpha omega, and here happens to be that is the formula of the eigenvector formula. So this is actually matching the definition of the eigenvector formula. So this part you can check here. So meaning that if we can solve the eigenvector, meaning that equivalently we can solve the original problems of the PCA, is try to maximize the variance of the projections. So that is the kind of the intuition of using the eigenvector to conduct the PCA here. This is not required in these PCA lectures, but you can also look into some more details. But unfortunately for the two textbooks, it may not present such kind of details. But for those, if you are interested in the theory, this is the theory behind the calculating the PCA here. And this is a way to only calculate the first principal component. And for the second principal component, then we need to make sure that the second component is orthogonal to the first principal component. And there will be another constraint, that is the product of these two vectors should be 0. So in our previous, like in linear algebra, if we know that the product of the two vectors is 0, means that they are orthogonal to each other and their angles between each other is 90 degrees. So that is the second problem of solving the second principal component. And when we look into the data points, we will see, say, for example, the original data points that we will talk about. If we find the first principal component, that would be the maximum spread. And the second principal component would be orthogonal to the first principal component. And usually we will only look at the first principal component, and in our later exams and tests, we are only requiring about calculating the first principal component. And that is the theory behind the PCA. It's not required, but you can feel free to check about this, about the theory and why we are using the eigenvector decomposition. So what PCA does is, first, it will center the data point X as the original. So Kai's question is, what does an empty sigma mean, like when the eigenvector of the bottom? So Kyle, what would be the specific questions, or which line are you talking about? Last slide? This one?
Oh, no, I mean,
This one?
Well, yes, that.
And which line are you?
Like it says, W2 is another eigenvector of sigma, and so on.
Yes,
Like there's nothing next to the sigma. What does it mean when there's nothing next to it?
nothing next to it. And
Like normally you'd see it next to a W. It means the sum of W over a certain range. What does it mean by itself?
oh, it's not sum, it's covariance. It's sigma. This is the covariance of the data point. It's not
Okay,
sum.
sigma on its own
Yeah,
is
it's
covariance.
covariance matrix. Yeah, we defined at the early slides that is the sigma that is equals to covariance. Say if we are talking about the covariance, variance is variance x and variance y and x y covariance and covariance. Yeah. So this is the covariance matrix. Sigma here is the covariance matrix of the entire data point. Is it possible to use 3 axes for a PCA? Yes, but sometimes we only look at the 2 axes because that would be easier for us to visualize the entire data point. It's possible that we will have multiple different principal components. Yeah, but let's move on to see.
Excuse me.
Yes.
The questions is the variance in the second component would be minimized or not necessarily?
No, because we are trying to maximize the
No,
value.
the maximums would be for the first component.
Yes, but for the second one is condition on the first one. We will need to find the second principal component that is orthogonal to the original first principal component, but we still need to look at another direction where the spread of the data point is maximized. Yeah, every step we only look at the directions which we can maximize the spread. So that's why the objective is still the same. But all those principal components, they should be orthogonal to each other. Otherwise, it will lead to a lot of problems. Say as we project to some dimensions or directions, they have some correlations, and they will lead to some redundancy.
I see.
So let's see how the PCA does. So we center the data point first because it will be easier for us to calculate the following values. So there's a kind of, we need to find out the means of the data points, and we use the original data set and minus the mean and use the projections. So the projection calculations, which is the eigenvector, that's usually done after we project the entire data point to the and center it as the 0 point. And then we will need to rotate it and try to figure out what would be the first principal component. So let's see the examples that's like the entire algorithms, and I will show you step by step with the simple examples. And the step is like a first that we will need to center the entire data point. We need to find the mean vector mu and the covariance sigma of the original data point. And then we compute the corresponding eigenvector and eigenvalue of these sigmas. And then we select the top k eigenvectors. And then we project the entire data point using the calculated eigenvectors and eigenvalues. And then we project to a new space, Z here. So the X is the calculated eigenvectors that we need to find, but we will see how those are calculated in an examples. So this is also required in our assignments and exams. So let's see an simple examples. We are given a data point X. This consists of 3 2D data points. First one is 1, 2, second one is 3, 4, and the third one is 5, 6. So each is the 2 dimensions. So first, we calculate the mean of the entire data set. So we know that the first dimensions, they are respectively 1, 3, 5, and therefore the mean is 3. And the second dimension is 2, 4, 6. The mean is 4. And for each dimensions, we minus the corresponding mean, and then we calculate the entire data set. It will be centered at the 0 point, and we can see the projected the centered data set will becomes the x minus the mean here. So it will becomes the -2, 0, 0, and 2, 2. So these 3 points, because each of these dimensions, it is minus, we remove the corresponding offset based on the mean. And then we calculate the corresponding covariance matrix A for the entire data point. So we can use the following covariance matrix. So for each values or each dimensions, we will calculate the corresponding mean. And we use the values minus the mean and use the product and divide it by the number of the data points. So please be aware we use the n-1 because we want to remove some of those bias. So say there's like we have the -2, 0, 0, and 2, 2. So because it's already 0 mean, so the mean is 0. So for each covariance or variance, we can calculate based on this formula, and we got the covariance matrix A here. So due to the time limit, you can feel free to dismiss, and also I will upload the video later. But if you, if it would be great that you can stay here and ask questions after I show the entire calculations. So suppose we are given this covariance matrix A here, and we let the determine this the A minus lambda I. So I is the identity matrix, and lambda is the eigenvalue that we need to calculate. So we already got the covariance matrix A here. So we calculate this part. That is we make the determine, that is the 4 minus lambda and 4 minus lambda for the diagonal one. Because the identity matrix, it have 0 for all those off diagonal elements. And therefore, we have 4 and 4 here. And we make the determine as 0. And therefore, we can calculate that is the 4 times 4 times 4, 4 minus lambda and minus 4 times 4. And we make the entire determine as 0. And therefore, we can calculate the corresponding eigenvalues, potential eigenvalue. So 4 minus lambda can be either 4 or minus 4. So therefore, the two potential eigenvalues, they will be either 8 or 0. So that is a way to calculate the two potential eigenvalues based on the given data, because it's a two-dimensional data point, and therefore we will have two potential eigenvalues here. And based on these two eigenvalues, let's see how we can calculate the corresponding eigenvector. So the eigenvector is, we need to look back the corresponding definition. That's the this formula. And we need to make sure that we can calculate the corresponding x here. X is the corresponding eigenvector because we are considering the two-dimensional point, and therefore this eigenvector should be also two-dimensional. And we can use some symbols to first define, say, x is equals to A and B, two dimensions. And then we use this formula because we already know that lambda can be either 8 or 0. So let's say we look at the lambda equals to 8 case, and we first look at this formula. So A minus lambda I would be equals to 4 minus A and 4 minus A for the diagonal elements, and the off diagonal elements, they are all 4. So it becomes minus 4 for the diagonal elements and 4 for the off diagonal elements. So this matrix is, so this formula can further be substituted with the new elements, and we have minus 4 times the vector we are interested, say the A and B. And we make it as 0. So please be aware it's 0 vector. So it's equals to 0, 0. So this formula, then we need to solve a linear systems or linear equations. So say there's minus 4a plus 4b equals to 0, and 4a minus 4b equals to 0. So they are all the same. So meaning that a should be equals to b. But with this, it does not necessarily help us to solve these eigenvectors. But please be aware, the theory behind the eigenvector decomposition and also the original definition of the problem, that we need to make sure the norm of the vectors should be 1, meaning it's the length of that vector will be normalized as 1. And therefore, we know that a to the power of the 2 plus b to the power of the 2 should be equals to 1, meaning that the vector, its length should be 1. And based on this two formula, a equals to b and a squared plus b squared equals to 1, and therefore we can calculate the a is equals to square root of 2 divided by 2. So that is equals to 0.707. And also a and b, they are all equal. A and b, they are all equals to 0.707. So that's how we calculate the first vector of these input covariance matrix. And similarly, for lambda equals to 0, we can also calculate another vector of the eigenvectors. And sometimes when we are using those Python libraries, it will return as follows. There's like 0.070 and 0.0070 and minus 0.707 and 0.707. So when it returns as follows, so the first column, we are usually corresponding to the first eigenvalues, which is 8 here. And the second column will correspond to the second eigenvalues. So please be aware about the output results of those PCA algorithm here. So after talking about the simple example, so in terms of the Python implementations, that you can call using the sklearn, and then you can call the corresponding decomposition. Actually, it will have the functions to the PCA, and you can decide the number of the components, and you can fit against the entire data set. And then after the fitting, then you can project the corresponding data set using this formula, and it will return the corresponding data projected. So one may wonder is how we can decide the number of the k, that is the number of the principal components. So we can use the so-called proportion of the variance, or the POV for short. It will be calculated like how much percentage of the covariance or variance has been described based on a certain k of number of the principal components. So typically we stop the search so we sort all those different eigenvalues from the largest one to the smallest one, and then we add one by one, and to see how the entire percentage of the variance is almost like a 0.9, and then we can conclude that is these components, they are sufficient for us to describe the variance of the data. And we can see some kind of the elbow points with some example. Say, for example, we can use the eigenvalues, and we can look at the values, and we sort from the largest one to the smallest one, and we calculate the corresponding proportion of the variance, or the POV, and we can stop the search of the k when we reach like around the 0.9, that is the 90% of the variance, and we can say that is this amount of components will be enough for us to describe the variance of the data. So this is a kind of way to select the k here. And when, of course, we can also describe the data points into a space, like we can project the data point into a 2D space based on the first two principal components. And then we can see these are all the data sets related to like digits, the handwriting digits. say we write 0, 1, and 2, and 3, and then they are all the images. And we use the PCA to project it into a 2D space. And we can see that some of those digits, they are close to each other, meaning that their patterns, they are very similar. So one can imagine, like, for example, like those 0 digits, they are very similar with the digit 6. And therefore, when we project it with the 2 principal components, they are very close to each other. That's why you can see there's the 0 and 6, they are very close to each other. So meaning that the mutual distance is preserved after using the principal component analysis. So due to the time limit, sorry, that is I could not further explain in very detail, but one of the interesting examples is the PCA for the Pokemon that I will recommend you to look at. So some people, they use the Pokemon data and feed to the PCA and analyze the patterns of different Pokemons. So Pokemons, they have like a HP, attack powers, defense, special attack, special defense, and speed. So different features, they feed this data set towards the PCA and check upon, like first they see there's like using the 4 components is good enough for us to describe the entire Pokemon data set. And then they further conduct some kind of the visualizations and look at the data point of the entire Pokemon data set. So interestingly, there is like when we look at like the first principal component, so here they project it and they look at the values. So here the values is the contribution of each attribute within this principal component. And for the first principal component, all different attributes, they are contributing with very similar values, meaning that when we are describing all those Pokemons, all those attributes, they are contributing, and that's how we can identify or differentiate different attributes. So that is a first principle that will preserve the variance of the entire data set. But for the other principal components, we also observe some interesting behavior. Say, for example, for the second principal component, if you see that some of the attribute is particularly contributing. So the larger value means that attribute is contributing a lot in the projections. And we can see there's like, we can observe 0.6 for the defense, but minus 0.7 for the speed. Meaning there's like a certain Pokemons, they may have very huge power in terms of defense, but pretty low in the speed. So some examples is like when we project the entire Pokemon data set into the PC1 and PC2, the first 2 principal components, some of the Pokemons, like say this one, this guy has the very high power in terms of defense, but pretty low power in terms of the speed. And for some other Pokemons, these 3, they are considered usually very good at the attack powers. And therefore, in terms of the PC1, they will have very high values, and they are all very powerful. But in terms of the PC2, it has very, very small values, meaning that they have very, say, less, in terms of the defense, it's not very, very remarkable. So there's a kind of the visualization that we can see some interesting behavior of the Pokemon here. And also another example, when we look at the third principal component and fourth principal component. So for the third principal component, we can see that there are some special defense because some Pokemons, they will have the special defense, and therefore their HP and their attack, they are all negatively contributing towards the principal component 3. So they will have the special defense here, and they are pretty powerful. And those Pokemons, they can be seen as these 2. So these 2 guys, their defense can be pretty strong. But in terms of like attack and HP, there's the health, they may be not very remarkable. But for the fourth component, there's for some other Pokemons, say these 2, probably you may be familiar with the Pokemon story. These 2, they have very good healing, or they could have very strong health powers. And therefore, they for the fourth principal component, the HP is contributing a lot for these false components. And that is why we can see this when we project the Pokemon dataset into the principal component 3 and 4, we can observe some other data points here. So from this example, one of the important takeaways is we can use the PCA to visualize the data into a 2D dimensional space. And therefore, we can also see some of those variants of the data set, and we can interpret the results based on their values. And the values, the larger values for the particular attributes may actually imply that some of the patterns of certain data points. So that is the basic takeaway for these interesting examples. And I hope that you can also have a look on this link later after the lecture. So that is the end of today's lecture. Thank you so much. And sorry, there's like a delay for here because due to the time limit. But I hope that you can take some time of the materials, and dimensionality reduction is actually very important and useful for many of those big data analytics. Thank you so much.